Bom dia. Good morning, everybody. It's time for us to start. So I will I have the pleasure to call for let's say, a welcoming address. Two people that represent metaphorically and metonymically the forces that are engaged in here. Of course, our first address will be to the World Cultural Council, who, of course, it's because of World Cultural Council that everything is happening. But for the welcome address, I will start by calling our rector, Amilcar Falcão, and then our host, Professor Paulo Pires. Professor Amilcar Falcão.
Good morning. Dear Director of Coimbra's Department of Culture and Tourism, Dr. Paulo Pires, Honorable President of the World Cultural Council, Sir Fraser Stoddart, 2022 laureates and speakers, students, teachers, and researchers from the University of Coimbra, from the high schools Infanta Dona Maria, Dom Duarte, and Avelar Bortero, from the College São Teotónio and Rainha Santa, distinguished guests, ladies and gentlemen. The University of Coimbra is extremely pleased and honored to host, for the first time in Portugal, the 37th World Cultural Council Award ceremony. The 2022 award ceremony itself will take place tomorrow in Sala dos Capelos and will be marked by the special solemnity of a great institutional act. But today, at São Francisco Convent Cultural Center, next to the Mondego River, an equally significant and important event is taking place: the special lectures of the World Cultural Council. Because of our commitment, your commitment and generosity, hundreds of students, education and researchers, as well as members of society in general, will have today the opportunity to hear the life testimony and benefit from the direct intellectual stimulus of exceptional speakers. This is the case of Professor Victoria Kaspi, winner of the Albert Einstein World Award of Science, who unfortunately cannot be present due to COVID, but will present a lecture by video conference. Professor Claudia Mitchell, winner of the José Vasconcelos World Award of Education, and Professor Ginny winner of the Leonardo da Vinci World Award of Arts. The three 2022 laureates will be joined by the lectures of two Nobel laureates: Professor Sir Fraser Stoddart, President of the WCC and Nobel laureate in Chemistry 2016, and Professor David Gross, Nobel laureate in Physics in 2004 and member of the WCC. It is in such examples of an outstanding professional and personal path that we all can find stimulus to overcome the challenges that accompany any process of growth and maturation. Because excellence is built on strong passions and genuine dedication. And it is also in examples of excellence that lies the inspiration capable of turning the most improbable dreams into reality. Let me conclude by expressing the wish that we can promote a culture of tolerance, peace and fraternity in a more sustainable world, as they are essential pillars shared by the common values of WCC and the University of Coimbra. Thank you for your attention. Have a nice day.
Thank you very much, Rector Amilcar Falcão. I would like now to introduce Dr. Paulo Pires, who is Director of the Department of Culture of Tourism from the Municipality of Coimbra, and of course our host. Please, Dr. Paulo Pires, the floor is yours.
Good morning for all. Rector of the University of Coimbra, Professor Amílcar Falcão, Honorable President of the World Cultural Council, Sir Fraser Stoddart, 2022 laureates and speakers, welcome. Students, teachers and researchers from the university and Coimbra, from the high schools Infanta Dona Maria, Dom Duarte and Avelar Brutero, from the colleges Santo António and Rainha Santa, distinguished guests, ladies and gentlemen. It is with great pleasure and honor that the City Council collaborates with the University of Coimbra in the hosting year in the São Francisco Convent of the present edition of the World Cultural Council Award Ceremony, by the first time in Portugal. And I ask you an applause for that. It's remarkable that this collective effort and energy between the World Cultural Council and the University of Coimbra that made possible this important and recognized event in the heart of the center of Portugal. Thank you all for that. It's also symbolic and significant that today and tomorrow this World Cultural Council will join the two riverbanks of the city, showing something that we all desire, a connected and unified territory called Coimbra, where the strength of the differences and singularities can guide us to a better future. Today, we received the special lectures of the World Cultural Council with inspirational guests in a unique place, where sacred and profane meet each other to celebrate the life of spirit, in the words of Paul Valéry. Without this powerful and, if you allow me the metaphor, without this love triangle, education, culture and science, life would be probably a big mistake. Thank you all for believing that we can do it, each one and together, here and now. Queria apenas também dizer algumas palavras em português também, se me permitem. Dar novamente as boas-vindas a todos, e, em nome da Câmara Municipal, aqui ao Convento de São Francisco. Vivemos tempos muito desafiantes nesta contemporaneidade. Tempos de transição, de mudanças, de adaptações, e quero muito sublinhar esta ideia também, tempos de sonhar mais alto contra a maioria das previsões e expectativas. Quase tudo à nossa volta, de alguma forma, nos impele a não arriscar, a não atravessar a pontos para a outra margem, mas ao mesmo tempo, numa espécie de inquietante dualidade que desenha os dias, estamos bem conscientes da urgência e da vitalidade de seguir em frente, de dar o salto, de ser criativo e imaginativo, que é, porventura, o ato mais revolucionário que podemos conceber nos nossos dias. E para isso precisamos da cultura como essa espécie de máquina de guerra contra o banal, o óbvio, o repetitivo, o expectável. O acolhimento da 37ª cerimónia da entrega dos prémios do World Cultural Council em Coimbra só pode deixar-nos felizes e orgulhosos, sendo de enaltecer aqui o papel da Universidade de Coimbra, primeira instituição de ensino superior em Portugal a receber este evento referencial. Dizer, para terminar, que o município de Coimbra está fortemente empenhado em estabilizar um pensamento e uma narrativa diferenciadores e potentes para este território, sendo que em janeiro do próximo ano, o mesmo ano em que se celebra, falava nisso há bocadinho com o nosso magnífico reitor, no mesmo ano em que se celebra o 10º aniversário da classificação da Universidade Alta e Sofia como Património Mundial da Humanidade pela Unesco. E, nesse sentido, iremos apresentar publicamente uma estratégia para a cultura em Coimbra entre 2023 e 2030. Nesse âmbito, é para nós absolutamente fundamental esta efetiva e contínua, e gostava muito de sublinhar estas duas palavras, efetiva e contínua, A articulação estratégica entre a autarquia, a Universidade de Coimbra e os demais agentes e players culturais, educacionais, sociais e económicos do Conselho e da região. Esta abertura empática e simultaneamente focada ao outro, a este movimento de olhar à volta, de olhar em redor, é essencial para desenharmos o futuro em Coimbra. Daí que o município e a Universidade estejam neste momento a consolidar uma plataforma de compromisso, de convergência e de colaboração em vários segmentos da área cultural, a qual salvaguarda, por um lado, as missões e objetivos específicos de cada uma das instituições, mas, ao mesmo tempo, estabelece aqui um compromisso coletivo em prol de uma cidade e de uma região que se pretendem abertas ao mundo. Fico muito contente, há bocado o vice-reitor Delfino estava a falar nisso, fico muito contente de ver aqui tantos jovens, né? Tantos estudantes aqui. Isso é de enaltecer, é de sublinhar. E diria, para terminar, e citando aqui um senhor que em 2023 vai estrear o seu próximo disco aqui no Convento de São Francisco, em Coimbra, diria que enquanto houver estrada para andar, a gente vai continuar. E acrescentaria que enquanto houver ventos e mondego, a gente não vai parar. Obrigado.
Thank you very much, Dr. Paulo Pires. It is now time to go to the special lectures, which will, of course, be all of them very special moments. And I would call Professor Constanza Providencia to present our first speaker, Professor Victoria Kaspi. Well, a couple of words also in Portuguese to warm up a little bit. Audience, muito obrigado pela vossa presença. A nossa primeira oradora não pode, infelizmente, estar presente como gostaria, como esperávamos até ontem, porque, infelizmente, por questões de saúde, por causa do Covid, que ainda paira por aí, não pôde viajar. Mas estará connosco com a sua apresentação e teremos a doutora Constanza Providência, que será o nosso profeta e intérprete para todas as questões.
Obrigada. So, thank you very much. It's very nice to be here at this meeting. It is with a great pleasure that I present Professor Victoria Kaspi, winner of the 2022 Albert Einstein World Award of Science. She holds a long-trotted chair in astrophysics and cosmology and distinguished James McGill Chair at McGill University and is director of the McGill Space Institute. Professor Victoria Kaspi has completed her undergraduate studies at McGill University and her PhD under the supervision of the astrophysicist Joseph Taylor at Princeton University. Joseph Taylor received the Nobel Prize together with Russell Herschel for the discovery of a pulsar, a neutron star that rotates in a binary. Victoria Kaspi has had an important contribution to our understanding of neutron stars, stars with extreme properties. Being a nuclear particle physicist, I'm very grateful for her contributions. In fact, neutron stars are the perfect laboratories to learn about dense nuclear matter, about the theory of strong force, quantum chromodynamics. But this is only possible if their properties are understood, if we are able to detect and interpret the information they send. The radius of one of these stars is not larger than 15 kilometers, although having a mass as large as 1 to 2 solar masses. And these objects may have periods of rotation almost as small as a millisecond. The fastest known pulsar was discovered with the help of Professor Victoria Kaspi and performs more than 700 rotations per second. She associated for the second time a pulsar to a supernova remnant that had been discovered in 386 after Christ by the Chinese. The prize is awarded in recognition of Professor Victoria Kaspi's fundamental contributions to our understanding of one of the most extreme forms of stars known as magnetars. Magnetars are neutron stars having the highest magnetic fields known in the universe, 1 million to 10 million Tesla. A normal neutron star has a field 1,000 times smaller. The Earth has a field of about 50 microtesla. In particular, she has shown that two types of stars, the soft gamma repeaters and anomalous X-ray pulsars, could be both explained as magnetars. A magnetar rotates slower than neutron stars and completes a period in 1 to 10 seconds. Presently, Professor Victoria Kaspi leads the CHIME. This stands for Canadian Hydrogen Intensity Mapping Experiment, the CHIME radio telescope in Canada, trying to understand another puzzle of the universe, fast radio bursts. She will be telling us about observations performed with this new instrument.
Hello, this is Vicky Kaspi, recording my lecture for the World Cultural Council in the University of Coimbra, because I'm not with you, having come down with COVID the night before I was supposed to board my plane. I was already packed. I was very, very excited to come. And I'm so sorry not to be there in Coimbra with you and not to see your beautiful city and your spectacular university, and not to be able to congratulate my co-honorees, Professor Claudia Mitchell, my McGill colleague, and also Professor Jamie Yoon in person for their awards, and other awardees. I'm so sorry not to meet Sir Fraser Stoddard, President of the World Cultural Council, and also very sorry not to be able to say hello to Professor David Gross, who I have known since I was a graduate student at Princeton University, and who was a very positive force at many stages of my career. I'm also very sorry not to be able to thank in person Ms. Lily Hernandez and everyone who has put so much effort into what I am certain is a spectacular event. But such is life, and as I sit here in my bedroom, hiding from my family to avoid infecting them, I'm very grateful for the technology that allows me to be with you even a little bit today. I will now tell you about the transient radio sky. And to do that, I would like to share my screen. The transient radio sky. Well, when people ask me what my research is about, I often say, I don't know, because I'm studying an object that is truly mysterious and we do not know what it is. And I hope by the end of this talk, you too will not know what these objects are, but at least will have a better appreciation for what the mystery is, and also will appreciate better some of the twists and turns that are involved in doing science at the forefront. You'll see there's a lot of surprises along the way as we try and unravel this mystery. The mystery of these short radio bursts that I will be telling you about, fast radio bursts, has captured the imagination of the press and the public at large. You can see here some examples of the sorts of press these objects have gotten. But really, I want to, before telling you about these objects and what we're trying to understand, I want to take a step back and remind us all about what most people think about the night sky. Here's a beautiful optical image taken with a conventional optical radio telescope of a constellation that some of you might be familiar with, the Orion constellation, the Hunter. You can see beautiful stars here. It's known as the Hunter from mythology, of course, hundreds and hundreds of years ago, which immediately tells you that people way back then saw pretty much the same object that we see tonight. The same stars are there. This configuration of stars, of course, they're not really related. Some are at vastly different distances than others. They just appear that way projected on the sky from Earth's vantage point. But this configuration is pretty stable. And if you come back 10 years, 100 years, 1,000 years, 100,000 years, you'll probably see the same thing on the sky. And that in some ways is quite comforting. Of course, all of these stars are just like our favorite star, the sun, in our own solar system. And we're very familiar with that object, and it's also comforting. It rises in the morning and sets at night, and it's always there. But you might not have realized that the sun itself actually is quite a variable place. This is a movie of our sun taken with NASA's SOHO mission in the light of an ultraviolet light. And you can see, first of all, the sun rotates. The sun has all sorts of interesting plasma effects going on, having to do with its magnetic field and variations in its magnetic field. It sometimes has huge eruptions. So stars are actually not stable and fixed permanently. They have interesting time variability associated with them. And, you know, we've known about this for many hundreds of years. In fact, Galileo himself, over 400 years ago, sketched out, this is a reproduction of a sketch that he made, the moons of Jupiter that he saw first with a telescope, realizing that they had orbits, that the planets orbit and things orbit the planets. There's dynamics, the dynamical universe. Things change when you start looking close enough. And with modern telescopes, we can see all sorts of variability on the sky. Here's one example. This is a movie, an artist's rendition of what we believe is how, if we could get really close to what we call a nova, that is one star that dumps material onto a second star, typically a white dwarf star, creating a thermonuclear explosion, which is witnessed as a very bright, great optical brightening, ultraviolet, sometimes X-ray brightening in the sky. We call that a nova. We see those, and these are very well studied on the sky. And that sort of explosion happens, it takes days to weeks. It will last. And then we know of other types of explosions. For example, we now can see, and we have directly observed, collisions of compact objects called neutron stars, very, very dense objects, sometimes found in binary systems. And here in this movie, you can see the system is, these two stars are approaching each other in their orbit, and soon they're going to merge in a huge explosion we refer to as a kilonova, a very, very large style nova. That means lots and lots of energy is released. And so there's many objects in the sky that explode or have instabilities that cause flaring or bursting. This is ubiquitous in the night sky, as astronomers have learned over the last several decades, and as I said earlier than that as well. Now, my talk is about the transient radio sky. And so let me tell you about that. But first, let's make sure, that we're all on the same page when I say radio. So most of you, I hope, know what this device is. I think very young people probably have no clue what this is, but I think most of us know that this is a radio. It's a device that has an antenna that detects radio waves that cause a current in the antenna that's then read into amplifiers and various analog electronics. This is the dial that allows a listener to specify a specific radio frequency to listen to. And you can think of the different frequencies, and here is the FM. This is 88 megahertz or 95 megahertz. These are like different colors of light, or of radio light, in analogy with the different colors that our eyes can see, which are also different frequencies. Here we have different frequencies, and you can adjust this. In this radio, you can turn a dial And you can tune so that you allow the speaker to emit only the signal that is coming at a specific radio frequency. And so that's what we're familiar with radio. But of course, radio waves are actually just a type of light. We're familiar with light in the visible range because that's what our eyes are sensitive to. And perhaps it's no surprise that our eyes evolved in that way because we live near a sun that produces predominantly visible light. But the full electromagnetic spectrum includes many other types of light that our eyes cannot see, but which we make use of. I mentioned ultraviolet before. We can't see it, but you're familiar with it being produced by the sun. X-rays, gamma rays, infrared light, microwaves, and radio waves, the lowest frequency electromagnetic waves that are used by astronomers. The lower the frequency, microwaves you're familiar with from a microwave oven, the lower frequencies are radio waves. And so when I talk about these bursts, which is what I want to tell you about, this mystery that I mentioned earlier, these fast radio bursts, these are bursts of radio waves that last only a few thousandths of a second. We are seeing them all over the sky. The first one was detected with this radio telescope. So you think many people, when they think telescope, they think of an optical telescope, but we also have radio telescopes that are sensitive to radio waves from the cosmos. And here's one of them. This is a radio telescope in Parkes, Australia, which detected the first such radio burst. And we believe that these radio bursts that last just a blink of an eye are ubiquitous. That is, if you could look everywhere on the sky all day long, you would detect upwards of 1,000 of these every day. And this phenomenon presumably has been happening for hundreds of thousands, millions, billions of years. But it's technology, modern technology, that's allowed us to be able to detect them only today. It's really driven by the computer gaming industry that has given us the computer power to be able to see these today. I'll explain more about that. But the bottom line is that these bursts that are happening all over the sky, their origin is unknown. We don't know what they are. And I can say for sure they're not microwave ovens, and that might perplex you why I'm saying that, but I'll explain shortly. So you might wonder, well, how do you see a radio burst? And here's an artist concept you'll see in some popular press. This is not how we see a radio burst. We can't see radio waves. We would need big antennas for eyes to be able to see them. So how do we see them? This is the first ever detected fast radio burst. We call it the Lorimer burst, named after the first author on the publication who reported it. And what you can see here on the x-axis of this plot, this is time. And this is just 500 milliseconds, that is half a second. And on the y-axis here is radio frequency, where using a radio telescope, we are sensitive to many, many radio frequencies all at once. And you can see this black horizontal line here. That is a television station that emits at a single radio frequency for all times. And the cosmic signal is this burst that's sweeping through the band that arrives at the highest radio frequencies first and slowly makes its way down to a few hundred milliseconds. That's not so slow, I guess, to the lowest radio frequencies. Now, I'm going to stop for one moment and pause the recording. Hello, I'm back. Sorry. if you've never had COVID, and this is my first time having COVID, my goodness, it's something. In any case, what I was trying to say is that this sweep we can correct for in software. So what you're seeing here is the digitization of the signal. We digitize it in time as well as in radio frequency, and we store these bits on computer disks, and we can correct in software for this delay across the radio frequencies. And that's what you see in the inset, is when we correct in software and line all of the radio waves up, we get a single burst. We get just noise, just garbage to start with, the burst that's cosmic, and then nothing after that. It goes away and it doesn't come back. That's a fast radio burst. And what I want to tell you is that by analyzing the amount of this delay, the degree to which it sweeps through, we call that the dispersion of the radio wave. We know that this event has come from far, far outside our Milky Way galaxy, and in fact, from a cosmological distance, meaning from an appreciable fraction, from appreciable distance that's an appreciable fraction of the scale of the universe. And that's a pretty bold statement. Let's all be sure we understand when I say outside our Milky Way galaxy, what I mean. Here is a picture not of our Milky Way galaxy. Of course, when you're inside your own house, it's hard to get a picture of the outside of it. So we can't get a picture of our own Milky Way galaxy very easily. But this is a galaxy probably not too similar. And we are situated on the edge of this spiral galaxy, of the Milky Way galaxy. Something like this, if this were it. And what do I mean by the size of the universe? Well, here's a graphic that shows different scales of the universe. Of course, the first, starting here, we're all familiar with the Earth and the solar system. And each time we're zooming out, the last image is shown in red, roughly the scale. So you can't quite, the Earth is just a speck here on the scale of the solar system. But we could zoom out further than that to the nearest, to the interstellar neighborhood, where our solar system itself is just a speck, and you see the closest stars to us. And then you can zoom out from the nearest interstellar neighborhood to the full scale of the Milky Way galaxy. And that's, you see, we're on the edge, as I mentioned, but that's, the Milky Way galaxy is just a little speck, as is the full neighborhood of stars around us. But you can keep zooming out of our galaxy into the local galactic group, where our galaxy is now just a smudge. You can see it here. And you can zoom out of our local galactic group, which, by the way, contains other galaxies like the Andromeda galaxy. And you can zoom out of the local galactic group to the Virgo supercluster. This is a supercluster of galaxies where groups of galaxies now appear as just a blob on this scale. And you can zoom out even further to the local superclusters, of which our supercluster is just one member, and the entire supercluster of galaxies itself is part of a group of superclusters of galaxies. And then you can zoom out even further, and here we reach the scale of the observable universe. Note that it's homogeneous. It looks pretty much the same everywhere. And we're just one tiny smudge on this scale here. And this is billions, the scale of billions of light years. And it's on this scale that we think these fast radio bursts are arriving from. Now, that's a bold statement. How can I justify it? Let me explain about dispersion of light. You're all actually familiar with dispersion of light. When you take white light through a prism, it splits it into the different colors of the rainbow, because white light is made up of those colors. The prism diffracts the light it spreads it out by different amounts depending on the frequency of the light. So different frequencies get spread in different ways, and this is responsible for the rainbow. Light from the sun passing through water droplets also, I said diffracts before, I meant refracts the light, so that the different colors come out at different locations. But what's also happening here is that the different colors are also traveling at different speeds in the material. And that's what another way of using the word dispersion. You might have thought that the speed of light is a constant. We see Einstein's famous formula, E equals mc squared. The c there is the speed of light. And you might think, well, that's a constant and it's the law and all light travels at the speed of light. But that's true, but only in a vacuum. Once you're inside a material, light travels slower than the speed of light. And for many materials, it travels at a speed that depends on its frequency. And that is what's happening with radio waves. Space is not a vacuum. Of course, you wouldn't want to go in space and try and breathe there because, yes, it's not a vacuum, but the gas there is very tenuous and you would indeed suffocate because there's not enough of the gases you would need to breathe. But it's not a vacuum. You can see with your own eyes, if you get a beautiful image, this is the Milky Way galaxy as we see it here on Earth. There's lots of dust, gas, stars, all sorts of things. And in particular, one thing that you can't see with your eyes, but which we know is present, are free electrons. The galaxy is filled with hydrogen gas, and a lot of that hydrogen gas is ionized, meaning that the electrons have been stripped off their protons, and we have many free electrons here in the galaxy. And it's those free electrons that disperse radio waves. And let me explain what I mean. Imagine here's Earth, and here's a radio telescope I will tell you about shortly, the CHIME telescope. And I'm going to produce a radio burst here, but show it in optical light so that you could see the colors of the rainbow. What you'll see is that all the colors are produced at the same time at the source, but then as they travel through this material, this gas, or these free, here meant to show free electrons, the radio wave, the waves get dispersed. So there's the bright source. It's all white. It's like it's white light. But then the colors get spread out because they're traveling at different speeds, and the highest frequencies arrive at Earth before the lowest frequencies. So I've shown you the fast radio burst source dispersing in that way in optical colors, but really it's happening to the radio waves. It's radio waves that get dispersed by free electrons. And so we know in our galaxy, so pretend this is the Milky Way galaxy again, this below it is a model for the distribution of free electrons in our galaxy. We know this, and this is well studied and well calibrated using other sources that are inside the galaxy, for whose distance we know, and we can see how much dispersion they suffer depending on how far away they are. So we've learned about the distribution of free electrons in our own galaxy. Here, this is the center of our galaxy, and we're over here on the spiral arm. And so we've produced models of our own Milky Way galaxy. And here it's, unfortunately, it's rotated. The galactic center, the center of our galaxy is here where the cross is. And this little thing that looks like Pac-Man, that's where the solar system is. And what you're seeing here are contours, like a contour map. But in this case, a map of constant total free electron, we call it the column depth. That is the amount of free electrons between us and a source in any direction in the galaxy. So if you look in this direction and the source is this far away, you have this is the quantification of how many free electrons you've had to travel through. And this is really actually a three-dimensional model. That is, it's not just in the plane of the galaxy, it's in all directions. We know how many electrons there are in any line of sight. In any direction, this model can tell us this. And in particular, it tells us the maximum number of electrons that are present in our galaxy to disperse light, to disperse radio light. In any direction, we know there's a maximum because eventually the galaxy ends. And then in the intergalactic medium, well, that's extremely tenuous plasma. There still are free electrons, but they're very tenuous. And so, coming back to the Lorimer burst and to fast radio bursts, the degree to which these radio waves are dispersed is way more than can possibly be explained in this direction of the galaxy. The maximum, we call it the dispersion measure, how much dispersion these radio waves have suffered. The maximum due to our galaxy is only 25 in these crazy units, not important, but only 25. Whereas this burst is so dispersed, its dispersion measure is 375, much, much higher than what the galaxy can produce. And this is what's telling us it's far, far outside our galaxy. And once you realize that these bursts are coming from far outside our galaxy, from great distances, to be able to detect them here, they must be extremely powerful events in the universe. It must be some sort of explosion where perhaps we're only seeing the tip of the explosion, the brightest moment of that, the brightest few milliseconds of that explosion. But it's extremely luminous to be seen across cosmological distances. Now, Lorimer and his colleagues found a few of these sorts of events, and then also at the Parkes radio telescope discovered some other events that looked a little bit different. And I want to tell you about this because it's quite interesting. This is an example of an event they found in their data. Looks very similar to the Lorimer event, except it's sort of clumpy and it has these kind of strange features, and it had other properties that were a little odd. And the Australian team started studying these, and they noticed a very interesting phenomenon. This is a plot showing time of day on the x-axis, where this is noon, local time in Australia. And this is the number of events they detected, where the gray ones are these strange sweeps, they call them the peritons, strange looking, didn't quite make sense. And the dark gray ones, well, those are events that didn't look strange. They had a nice uniform sweep. And it's very curious that the peritons all occur or mostly occur around lunchtime. And that was what we call in science suspicious, because the cosmos should not know when it's lunchtime in Australia. And indeed, it turned out that a periton is produced whenever the telescope was pointing at the visitor center where there's a microwave oven. And if that microwave oven was being operated and was opened prematurely by a very hungry and impatient user, it would produce a periton. And it's actually a graduate student who stood there, opening and closing the microwave oven with the telescope pointed at it, and proved that the peritons were actually the microwave oven, the local microwave oven. And why am I telling you this crazy story? Because I'm so proud of the scientific community, which published in one of the most prestigious journals in astronomy, the monthly notices of the Royal Astronomical Society. They identified the source of peritons at the Parkes radio telescope as being when a microwave oven door is opened prematurely. And so this was, I think science is wonderful. When we're wrong, we say it, and we admit it publicly. We publish our results. And also this had the result that we then could feel confident that the dark gray ones in that plot, the sweeps, which are not distributed in any special way in the Australian day, as a cosmic event should be, that these are excellent candidates for genuine extragalactic transients. And indeed, they were right. We've now been detecting FRBs at many different radio telescopes, as I'll describe. And, you might say, okay, what are these things? Could they be exploding stars like some of the ones I showed you at the start? Could they be colliding neutron stars? Could they be a neutron star colliding with a black hole? And I'm listing these possible models because these are all in the literature. For a while, there were more models for what FRBs are than there were actual events detected. But there's many, many possibilities. And I put the bottom one, magnetars, as one in blue, because it's one of the leading models. So one question I get asked frequently is, well, what's a leading model for what fast radio bursts are? And it's magnetars. So what are magnetars? Magnetars are observed in our own galaxy, ultra highly magnetized young neutron stars, very, very dense object, where the magnetic fields are the highest known in the universe and are unstable, so that the star will occasionally, and here I mean every few years, explode in a giant burst of X-rays and gamma rays. And these are observed ubiquitously. In fact, I worked on magnetars for many, many years. So I could talk your ear off about magnetars, but I'm holding back here because magnetars were not known for very large radio bursts. They're known for large gamma ray and X-ray bursts, but not for large radio bursts. So some people thought there's enough energy there to produce these radio bursts, but it's a phenomenon that has not been seen from magnetars. Just hold that thought. Now, you might say, why don't you just go and look where the fast radio burst is coming from? See where it is. What type of galaxy is it? Is it in a young galaxy? Is it an old galaxy? See where it is in the galaxy. Is it at the center of the galaxy? Is it at the edge of the galaxy? Those could be clues to what these objects are. But there's a problem. And the problem is that radio telescopes do not pinpoint locations of sources very well. So the Parkes telescope that discovered the Lorimer burst and a few other many other fast radio bursts, it can only localize on the sky to within a region that's extremely large, which contains literally thousands of galaxies. So you can't possibly know which galaxy it came from, never mind where in the galaxy it came from. And you say, well, oh, that's too bad. How can you beat that? How can you do better? Now, it turns out you can go to a larger telescope. And for a long time, the largest telescope in the world was the Arecibo telescope in Puerto Rico. It has ceased operations, but it is a 300-meter telescope. That's very large, several football fields across. And still, you would find hundreds. That is the localization region of a much larger telescope, the largest telescope on Earth. Still doesn't do the job. There's still many dozens of galaxies in there. In order to pinpoint the galaxy, you need what we call an interferometer, which is an array of many, many radio telescopes, all observing in tandem and separated sometimes by kilometers, or even hundreds of kilometers, or even thousands of kilometers, interferometers. And for example, the 25-kilometer baseline, we say that the separation of antennas, the largest separation of the very large array telescope in New Mexico in the United States, it can pinpoint. And so you might say, why don't you go to the very large array telescope and look and see and find a fast radio burst so you could pinpoint. The problem is because you don't know where or when these events are going to go off. They're transient. You can't predict it. So you could point the very large array for 10 years and never see a single burst because its field of view is tiny. The burst is happening over here. So it's a problem. Now, let me tell you about the Arecibo Observatory. I mentioned it's in Puerto Rico. This is a 300. It doesn't function anymore. It actually suffered a terrible collapse. You can see this online if you want to see the very sad, disappointing collapse of the Arecibo Observatory. But when it was functioning, this is a 300-meter aperture. This is me at the top of the aperture here. If you zoom in, my knuckles are white. It is frightening. It was frightening up there. This is the catwalk that you walked up. This is a catwalk. This is a 3-story visitors center down here, just to set the scale. In any case, that's the Arecibo Observatory. Those are a couple colleagues of mine. And we just started detecting, we were doing a survey for these objects, and we detected a fast radio burst. This is the first one we detected. And you see here the telltale sweep as a function of time, the radio wave sweeping in. Here is correcting for the dispersion, the de-dispersed burst. You see a lovely burst. And to our amazement, we sat there and continued to observe with the telescope this region of the sky. And it was actually my student that discovered, my student, Paul Schultz. Here's a picture of Paul Schultz, PhD student at the time, discovered that this burster repeats, unlike any of the Parkes ones before it, which would burst and never come back. This one, we waited and waited, and in 1 hour observation, we saw 10 more bursts from it. And here they are. In this case, we've already removed the dispersion in software, but they're all dispersed by the exact same amount. And we were just absolutely shocked that these bursters can repeat. Because if you imagine a model where they're colliding neutron stars or colliding stars of any kind, they're not going to collide 10 times in an hour. And then we've seen this thing 1,000 times since. So that just immediately ruled out a whole class of models. It was a shock to us. And you can see we got lots of press about it again. And the amazing thing is it immediately ruled out a class of models, but also allowed us to now go and propose to an interferometer, the Very Large Array in New Mexico, because we had a place to point. And we could say there's something there. And if you wait long enough, you're going to see it and you're going to localize it and we'll see what kind of galaxy it's coming from. And we did this experiment. We had to ask for the time. We went there and we sat there for 60 hours, which is a lot of time on the Very Large Array. And we saw no bursts. The sky was not cooperating. But we were very certain of ourselves and we kept asking. And in a test observation, several months later that they gave us, boom, in this radio image taken with a Very Large Array, you can see that these circles are the error regions from the Arecibo telescope. We knew it was somewhere in these two circles, and bing, this is the location of the radio burster, which was detected with the Very Large Array with the same amount of dispersion. And this is, by the way, technically very challenging at a telescope like the Very Large Array, but we had it localized. We knew we could pinpoint it on the sky, and then we could go to an optical telescope and look and see what galaxy was there. So we actually, with the VLA, we didn't just catch one burst, we caught 9 bursts. It turns out this thing doesn't burst randomly. When it's active, it's producing lots of bursts, and then it'll be dormant for months. That's a clue to what it is, but we don't know what it means. Interesting, isn't it? Interesting. I find it interesting. I hope you are finding this interesting too. I can't see your faces, so I don't know. In any case, we went with the position from the VLA. We went to the 8-meter Gemini telescope in Hawaii, one of the largest optical telescopes. And this is the optical image. We got this blue square down here. We were shocked again. It's, like I said, this story has many twists and turns and surprises. You never know what's going to happen in science. We were shocked. We were expecting a beautiful spiral galaxy of some kind, or perhaps an elliptical galaxy, a nice large galaxy. Instead, it turns out this object was in a tiny little dwarf galaxy. You could barely see it. And it turns out there's many dwarf galaxies in the universe. So they're quite common in the universe, but they don't contain much mass. Most of the mass is not in these things. But the good news was, so this was a puzzle, why in a dwarf galaxy? But the good news was that we could measure the distance to the galaxy. Once you see the galaxy, we have techniques. It's called measuring the redshift, for those of you familiar, but don't worry if you're not. We knew the distance and we could confirm that it was indeed at a cosmological distance, as our arguments about dispersion measure had indicated. So it was very gratifying that science was working, that we thought we understood about galaxy dispersion. And indeed, when we finally pinpointed this first fast radio burst source, it was in a galaxy that was far away. And we got lots of press. The New York Times reported it was traced to a faraway galaxy, but the caller is probably ordinary physics, which was amusing because I don't think this is so ordinary, but never mind. Meanwhile, a different newspaper in New York reported that it could be aliens. And I just want to say here and now that we do not think this is anything but a natural phenomenon. Just have to get that out there. In any case, where did we stand pre-2019? I'm not 100% sure about the time I have left, so I want to at least take a few more minutes to tell you where we stand today. As of 2019, it was clear one fast radio burst repeats, and it ruled out colliding stars for this source and anything that can't repeat. And it enabled the first sky localization, but it left many questions unanswered. Do all FRBs repeat? What is the bursting source? Why is it in a tiny galaxy? It was just clear we had to find more. And so we had to find more of these objects. So now I want to tell you briefly about the experiment that we're doing now in Canada, the CHIME telescope. This is a radio telescope. It stands for the Canadian Hydrogen Intensity Mapping Experiment, which might immediately tell you that it was designed for a totally different purpose, and it was. It was not designed to study fast radio bursts, but it turns out it's phenomenal at doing it. I'll explain why. This is a very unusual geometry radio telescope. It's made of cylinders. Each is 100 meters long by 20 meters wide. So the total area of this telescope is about equal in Canadian units to 5 hockey arenas. I love to make that joke, but really this is high-tech stuff. This is a transit telescope that is always looking up. It has no moving parts. And on each axis of each cylinder, there's 200 hanging there. There's 256 antennas that are all being read and digitized extremely fast at extremely high data rate into sophisticated computing infrastructure located both under the telescope and to the side of the telescope in these specially custom designed shipping containers. The input data rate from all of these antennas into the telescope, into what we call the correlator of the telescope, is 13 terabits a second, which is equivalent to the world's, roughly equivalent to the world's cellular network, all cellular networks combined. This is a very technologically challenging project, and you can see here, first of all, the scale of the project. This is a bunch of team members standing along the axis, just to show you how large it is. And this is a diagram showing you the different cylinders and how they go into these boxes, which do digitization and frequency analysis using field programmable gate arrays into another set of computers that analyzes the data and produces spatial beams on the sky that allows us to search for fast radio bursts. These are made of gaming computers, GPUs as we call them. And then the search engine that search for fast radio bursts is made of conventional, about 130 computers that are all constantly searching in real time for fast radio bursts all over the sky, at the same time as we are making maps of the sky in neutral hydrogen, and also even studying another astrophysical object called pulsars. You can see, yeah, I explained this, that the start of the beginning, the first portion of the correlator is under the dishes. You can't see it. There's a house, there's a little hut there that you can walk in, stand. You could have 10 people in there if you wanted. And these are shipping containers that have the fast radio burst engine and the X engine. And these are some of the students and postdocs who are responsible for building this telescope. This is very much this is my student, Ziggy Plenis, and other members of the team who've worked very, very hard. Lots of cables involved here, building antennas, and here are the computers. You see, it's a very sophisticated experiment. And so why is it so good at fast radio bursts? The Parkes telescope, it's a spherical aperture. It can see a tiny region of the sky only. And so most of these transients events are happening in different places, and this telescope can't see it. Sometimes it gets lucky, and so it's able to detect a few. But for the most part, it doesn't see the vast, vast majority of fast radio bursts on the sky because its field of view is so small. Now, a cylinder, on the other hand, it only focuses in one dimension, and so it sees a massive swath on the sky, several hundreds of degrees. And so this is orders of magnitude greater field of view that enables it to catch more of these transient events. If you compare the field of view of the cylinder to the field of view of a circular aperture, you see it's orders of magnitude larger, which allows it to detect orders of magnitude more events. And so as the sky rotates overhead, you see we have a much greater chance of detecting these transient events. And that's why CHIME is such a powerful radio telescope for fast radio bursts. And indeed, as soon as we turned it on, we started detecting them, and Nature magazine wrote us up, very exciting. This is a histogram of the number of fast radio bursts that have been detected up until 2019 by different telescopes around the globe. Here you can see the gray ones are the Parkes telescope. There's other telescopes. The Arecibo telescope found a couple. But when CHIME turned on, this is the number of fast radio bursts that is now known, and this is in 2019, of the pace has continued. Because of our enormous field of view, we are detecting hundreds, and in fact, by now thousands of fast radio burst sources, and allows us to study the phenomenon in great detail. And so we have discovered now literally dozens of repeating fast radio burst sources. We're uncovering a whole population on the sky. And because you have dozens of these events, you can now discern interesting properties that, for example, the repeaters, it turns out their bursts tend to be on average a little longer than those of the non-repeaters. The range of radio waves that they produce, the spectra, are also a little different. We're starting to, when you have a population, then you can do some very interesting science and gives you clues to what these things are. Perhaps repeaters are a different class of fast radio bursts. Maybe there's many things in the universe that could produce fast radio bursts. We also, one of the major discoveries our group made was detecting a very luminous radio burst from a Milky Way magnetar, from a magnetar in our own galaxy. And you can see it was actually two very, very bright bursts coming from our own galaxy, which immediately suggested, this is why it's the leading model for fast radio bursts. We've seen one produce for the first time a radio burst that was sufficiently luminous that had it occurred in a nearby galaxy, it would have looked just like a fast radio burst. That was super exciting, and I'm going to show you plots a little technical, because and bear with me. For those of you, what I'm trying to show here is this is brightness on the y-axis and distance on the x-axis. These are galactic sources that we've known and studied. These are all in our galaxy. Here's the magnetar burst, extremely high brightness, luminosity inside our own galaxy. These are fast radio bursts over here. These are lines of constant energy. And so the point is that this source nicks the bottom of these uncertainty regions for fast radio bursts that are the weakest fast radio bursts. So the magnetar was as bright as the faintest fast radio burst, but there's many more, far, far more energetic fast radio bursts that we have observed. Are those also magnetars? We don't know. That we don't know. We can say some fast radio bursts are magnetars. We can't say they're all magnetars. So wrapping up the CHIME Fast Radio Burst project, we have lots of fast radio bursts. We are analyzing them all. We are learning so much about the population, both by finding individual interesting sources like the galactic magnetar and some others that I don't have time to tell you about, and by studying populations of these objects and seeing statistical differences between subgroups. Very, very interesting. And in summary, these objects, they're still mysterious. I can't tell you what they all are. Some may be magnetars, but we don't know if all or even most are. Some repeat, could be multiple classes of objects. And the CHIME telescope in Canada is helping to solve this mystery. The last point I want to make is just that even if we never figure out what these objects are, even if we never figure out what they are, I haven't had time to describe it to you in this talk, but these fast radio bursts are fantastic probes of the universe, the cosmic web of the universe at its largest scales. The radio waves probe and give us fantastic novel information about large-scale structure in the universe. And so even if we never figure out what they are, we are going to learn a tremendous amount about the universe just by studying fast radio bursts. And so with that, I say thank you very much for your attention. And I'm, again, so sorry I couldn't be there to answer questions. If any of you has a question you'd like to ask, please feel free to email me. And I hope that you have a wonderful rest of your day. And the rest of the talks are interesting. I'm so sorry I can't be there. Thank you very, very much for your attention.
Thank you very much for your applause. I'm sure that Professor Kaspi felt the radio effects of the audience here while she's making her recovery in Canada. And now we are going to move to our second speaker before the break. And I would call my colleague, Professor Cláudia Cavadas, to present Professor Sir Fraser Stoddart, who will be our next and face-to-face speaker.
Wow, what a moment. So good morning, everyone. It's really a pleasure to be here with you to present you Professor Stoddart, next speaker. So let me put my... So Professor James Fraser Stoddart is President of the Direct Board of the World Cultural Council and received in 2016 the Nobel Prize in Chemistry for his pioneering research on supramolecular chemistry and molecular machines. Professor Fraser Stoddart received other numerous awards for his work. Namely, in 2007, he was awarded with the Albert Einstein World Award of Science. Professor Fraser Stoddart has a long and outstanding international scientific career with more than 1,000 scientific papers dedicated to chemistry. Professor James Fraser was born in Edinburgh, in UK, but I'm not going to describe his outstanding and inspirational life and career because we will have the opportunity to listen to his conference entitled Around the World in 80 Years. But I would like this opportunity to highlight only two major contributions of Professor Fraser Stoddart. One major contribution, so the first one, Professor Fraser Stoddart dedicated decades to produce new knowledge in the field of chemistry and generally to fundamental or basic science as so important as chemistry. We do know that basic science are vital to attain sustainable development and to improve the quality of life for people all over the world. The achievements of fundamental sciences should be better communicated to everyone. That's why this year, from July 2022 to July 2023, the UNESCO recognized this is the year of International Year of Basic Science for Sustainable, that recognized the relevance of fundamental sciences. So thank you, Professor Fraser Stoddart, for your contribution to chemistry, a fundamental or a basic science. The second major contribution that I would like to emphasize and acknowledge, Professor Fraser Stoddart has been promoting science around the world and helping other researchers. And the numbers, the round numbers are really incredible. During these 50 years of career, Professor Fraser Stoddart helped or mentored or supervised more than 500 early researchers from maybe 50 different countries. So Professor Fraser Stoddart helped those researchers to cultivate their independence and unique strengths. So the Nobel laureate, Sir Fraser Stoddart, used to say this. Let me read. Science that changed the world is a product of investing time in being a good mentor to young researchers and encouraging them to think outside of the box. So again, thank you, Professor Fraser Stoddart, for your time and contribution to science and to inspire new generation of scientists. Maybe some of them are here already. So the floor is yours. Thank you so much.
Bom dias. Good morning, everyone. It's a real pleasure to be standing up here at the podium. And my first very pleasant duty is to thank Vice President or Vice Rector, I should correct myself, Cláudia Cavadas, for her very inspired introduction. I would also like to take the opportunity to thank the people behind the scenes here at the University of Coimbra for putting on this absolutely spectacular show in a stupendous setting. I also would like to extend my congratulations to the three 2022 WCC, World Cultural Council laureates. All of you, my congratulations, very well done. We've heard one talk. I look forward to hearing the other two talks. And I'm also, I think, honored that I'm sharing this podium today with a fellow Nobel laureate in physics, Professor David Gross from the University of Santa Barbara. Okay, so I'm going to start my story around the world in 80 days. Your patience, take two. I hope it does work now. Here we go. So the story begins in 1942, the middle of World War II. I am taken at the age of 6 months to this remote farmhouse, about 12 miles south of the capital of Scotland, namely Edinburgh. And here is the view that I cherished from my bedroom window. I just want to point out that that's a horse trough. This is my father and a sheepdog. There was a huge transformation during the 25 years that I spent on this farm. We went from horses and carts to tractors and combine harvesters. So down on the farm, I was an only child, highly supportive parents. They sacrificed a lot for my schooling. We had no electricity until I was going to university at 18. It was a mixed arable farm, but we were free to run wild, to invent games, to risk-taking was encouraged. Okay. Thank you. Of course, being on a farm, one learned to work, and there was always good reward, good food for effort. Now, I went to a village school for some 4 years. It was one of those schools where there was one schoolmistress for the whole of the school. We were 5 when I went. We were 28 when I left to go to this college in Edinburgh, where I had a great general education. I have to say, terrific teachers. Pillar box red uniforms with black trim. Sports were emphasized, and there was also some army training. The subjects that I was exposed to included all of these ones, and also some music into the bargain. In 1960, after 10 years at school, I went to Edinburgh University and studied chemistry, taking my PhD degree, having studied a natural product called gum arabic from the Sudan, its structure thereof, and there was a small research group I was part of, and you can see quite a handsome young man on the right-hand side there. My professor, when I left in February of 1967 to go to Canada, his last parting words were, "Stoddart, whatever you do, identify a big problem." And I was a bit confused. I wasn't quite sure what he had in mind. So I take off to Canada via Montreal to Kingston, Ontario, and arrive and join a somewhat larger group. And here is my mentor at postdoctoral level, Ken Jones. He announced within a very short time of my arrival that he was going to Brazil, to Curitiba. And I assumed, well, this would be for a couple of weeks, but no, this was for 1 whole year. So he disappeared, and the Canadian Postal Service went on strike, so we had very, very little communication, and I was left to do my own thing and search for that big problem. And I was very lucky because within 6 weeks of arriving, I went to the chemistry library and I stumbled across a paper by someone that I had never heard of, Charles Pedersen. You'll see he was to share the 1987 Nobel Prize with Donald Cram from UCLA and Jean-Marie Lane from Strasbourg. But in this very short communication, Pedersen described the synthesis of a very unusual compound at the time. It was an 18-membered ring with 12 carbons and 6 oxygens. And I had been instructed at Edinburgh by my undergraduate teachers to forget about making rings any bigger than 6, 7, and so forth. So this was maybe my big problem that I was encouraged to tackle by Professor Hurst. And so I get going in my own way at the research in Canada. And here is a compound, it's called alpha-cyclodextrin. Microbiologically, it can be obtained in ton quantities from starch, effectively from corn that grows in the middle of America, and is very inexpensive. It's a circular compound. Treat it with 4 reagents was one of the first things I did. I should say, in chemical parlance, it has 6 times 5 stereogenic centers. So that's 30. And these 4 reactions wipe out all chirality, all handedness. It has no optical activity. And it's a very large ring, 30 in size with 12 oxygens. It didn't do anything, but it introduced me to a field that became known as supramolecular chemistry. Before I left Queen's University to return to the UK in 1970, and this book was published in 1971, I had started to write it when I was at Queen's, and I finished it at Sheffield. One of the eminent stereochemists of the day, Ernest Eliel, then at Chapel Hill at the University of North Carolina, was a great supporter. He read the whole manuscript, covered it with red ink, and saved my bacon. However, the professor that I met in organic chemistry at Sheffield did not turn out to be so supportive, and I eventually worked out that he was probably resentful. I shouldn't be writing books. So it was a rather difficult time. I didn't see my first graduate student until 72. Teaching was not easy. It was a stressful existence, but I did begin doing some research. And that research involved the marriage of, again, carbohydrates, this is glucose here and here, with the crown ethers that Charles Pedersen had introduced into the chemistry literature. And this marriage between crown ethers and carbohydrates, despite the fact that I was not having a wonderful time at Sheffield, didn't end up by quelling my enthusiasm for chemistry. You can see that my 2 daughters here, Fiona and Alison, 6 and 3, are standing in the middle of an 18 crown 6 with a carbohydrate on the side and a potassium ion in the middle. So here I was building sandcastles on the beach at Edinburgh. So this period came to an end around 1978. I wrote up a review, and the one quote that I want to bring to your attention is one from Nobel laureate in 1975, Vladimir Prelog. Chemistry differs. Maybe I have to go to read this carefully. I'm sorry about that. It's too far away. All right, chemistry takes a unique position among the natural sciences, for it deals not only with material from natural sources, but creates the major part of its objects by synthesis. In this respect, the potential of its creativity is terrifying. So that was the take of Vladimir Prelog, which I totally agree with. And so does Marcel and Berthelot back in 1860, who made the comment that chemistry creates its own object. Now, let's go on and appreciate that in research at Sheffield in this first period, I'd married crown ethers with carbohydrates. I think I'd learned to be imaginative. I met the other major influence in my life from UCLA, Donald Cram in New York in 1976. He turned out to be incredibly supportive, so much so that I spent 3 months at UCLA in the early part of 1978, and he helped me arrange to leave academia and go into industry, Imperial Chemical Industries, corporate laboratory in Runcorn, Cheshire, in the west of England for 3 years. This move turned out to be not just a relief from what was not a very pleasant department, it was a breath of fresh air. I was surrounded by talented scientists. The laboratory was extremely well equipped. The spirit was one of collaboration. I joined a group called the Catalysis Group, met a few people, including Howard Colquhoun, that I'll introduce you to, took up an area that we kind of invented called second sphere coordination, and that led to the use of 2 wipeout weed killers that were marketed worldwide as a 50-50 mixture, much of them coming to the United States to remove the green from potatoes in Idaho before they were, as it were, harvested. Another person I met was a first-class crystallographer from Imperial College London. And belatedly, I learned some management skills at the university. So looking at this area of second sphere coordination, the master of first sphere coordination was a Swiss chemist, Alfred Werner. He was a Nobel laureate in 1913. And one of his disciples in the UK was a man called Joseph Chatt. And here's a little bit of Chatt's philosophy. Since scientific discovery is not yet predictable, so he tells us, if you have an exciting road to follow, do not be put off by those who say there is nothing at the end of it. They do not know. Persevere and enjoy the excitement of exploring the unknown. And that's exactly what we did. Here is Howard, and here is David, and the graduate student in London that brought about this transformation in second sphere coordination. And what do I mean by that? Well, these blue L1s was what Werner brought to the world. What we added on were weaker interactions, the red L2s, around the outer sphere of a transition metal. And the X-ray crystal structure you see here, the yellow is platinum. The ligands that are pointing down are 2 ammonium ligands, and there's a bipyridine in the upper half of the ball and stick representation. And you can see how beautifully it turns out that something called dibenzo 30 crown 10 wraps itself around this transition metal complex. There's some other renderings of our discovery in the period of 1981, and it didn't take much imagination to remove the platinum and take up the challenge of complexing diquat, the first of the 2 wipeout weed killers that I am drawing your attention to. that were presented to us effectively on a plate because of my presence at ICI. I had intended to stay in industry, but imperial chemical industries started to fold up about 1981, and so I had little option but to go back to the chemistry department at Sheffield. Little had changed, but I was more mature. I was able to handle much of what was going on with growing confidence, and while I found little support locally for trying to do something about department that was not working well, I criticized the system nationally, and that did not win me many friends or supporters. Another thing that did not win me many friends was I hired foreign students from other parts of Europe, from Italy in the first instance, here in Portugal, Spain, and so forth. And this was frowned upon by the senior people at Sheffield in the chemistry department. But I did find, nonetheless, supporters, and research thrived, and it set the stage for breaking into a branch of chemistry that we called mechanically interlocked molecules. And so this involved the introduction of a brand new bond into chemistry called the mechanical bond. And if I make the point that probably thousands of chemical compounds are made in laboratories all over the world every day, maybe a dozen new chemical reactions are invented every year, but it's only once in a blue moon that a new chemical bond comes on the scene. And so we were privileged to be able to participate in that advance. And our first so-called catenane, which I'll describe to you in a minute, was published in 1989. My late wife and I ran many conferences, but come 1990, for various reasons, I was ready to leave Sheffield. Before I go to my next port of call, I want to point out that we had complexed dicot, one of these bipyridinium-based wipeout weed killers with dibenzo 30 crown 10. We had failed to complex paraquat, which you see on the left-hand side here. And eventually, after spending a lot of time that did not add up to very much, we found that a compound called BPP34C10, which is an acronym for bisparaphenylene 34 crown 10, so it's a 34-membered ring with, again, 10 oxygens. It's a constitutional isomer of dibenzo 30 crown 10, and it bound paraquat very well. Having put blue inside red, we had to find out how to put red inside blue. So there followed the design and synthesis of what became known as our little blue box. And while the crown ether complexed being pi electron rich with pi electron deficient guest species, the little blue box being pi electron deficient complexed with pi electron rich guests. And so here you see a movie of paraquat finding its way inside the bisparaphenylene 34 crown 10. We were able to then use the information that templation was important to make the little blue box in high yield. And so you'll see that this red component acts as a template around which the blue ring builds itself. And what you've been looking at is the run-up to us being able to use this chemistry to make mechanical bonds. And the two best known mechanically interlocked molecules are the catenane on the left and the ritaxane on the right. The catenane is an example of two interlocked rings minimally, can be many more, and a ritaxane is a dumbbell with big, big stoppers with at least one ring in the middle. And that could be summarized, as I say, the two of them as being examples of mechanically interlocked molecules, or MIMs. And the names are derived from Latin, in the case of the ritaxane, as you can see there, and also Latin in the case of the catenane. So we were set up by the end of the 80s to use what I call donor-acceptor templation. That is the weak interactions between an acceptor, the blue component, and a donor, the red component. And if we mix these together in acetonitrile at room temperature, then we got our, I guess, big moment, our microwave moment, if I can just play back to the previous talk. We obtained a 2-catenane in an amazing 70% yield. This represented a jump from 1% to 70% overnight for making an all-organic catenane. And it appeared in the cover of Angewandte Chemie in October of 1989. Here is a movie showing you how it comes together. So the ring, the red one, acts as a template for the making of the blue ring. The interesting thing is that the interactions between the red and the blue live on in the two rings after they've been made. And so we could use proton NMR, that's nuclear magnetic resonance spectroscopy, to detect rocking, pirouetting, and also circumrotation, all occurring at different rates. The first fast and the last one relatively slow. Here's a photograph of the person that introduced me to UCLA, Don Cram and his wife Jane, and my late wife Norma, at a meeting, a big one, in Sheffield in 1991. So what happened after the 80s? I moved to Birmingham University in 1990, and I was there for 7 years. I had been headhunted, despite the fact that I was a big critic of the British system. They put a big investment into literally saving their chemistry department, which had fallen on bad times, and I became a professor at the age of 48. I had excellent students, most of them coming from other European countries and Asia, even America. New laboratories, state-of-the-art equipment, and research really blossomed. And we described our first so-called molecular shuttle in 1991, followed by a molecular switch in 1994. Another breakthrough was a 5-membered catenane, which we called Olympiadane for obvious reasons, in '96. And during my last 4 years at Birmingham, I was head of the School of Chemistry. Change was dynamic. And just to give you an academic tree, Birmingham had a glorious past in carbohydrate chemistry in particular, thanks to the creativity of Sir Walter Norman Haworth, who was a Nobel laureate, the first British organic chemistry to be honored in Stockholm in 1937 for his synthesis of vitamin C and work on polysaccharides. And you can see that his training took him back into the heydays of German organic chemistry. And after a couple of people, my mentor in Edinburgh and in Queen's, of course, I fell in love with or fell foul of the medal that the others earlier on in my lineage had received. Now to the chemistry again. A degenerate 2-ritaxane, I call it, was described in '91 using the same principles that had been employed to make the catenane. and the weak interactions were exactly the same. Weak hydrogen bonding, donor-acceptor interactions, even weaker, and extremely weak so-called CH-pi interactions. This time, the yield of the first reaction was about half that of the catenane, because it's a less organized system, although I should add that both of these nowadays can be made in quantitative yields. And again, you will see this movie that shows how the little blue box clips itself around a dumbbell. Once you have the dumbbell, you can watch the ring move back and forth by, again, NMR spectroscopy, and it does so in acetone solution about 2,000 times a second. And this molecular shuttle, which again you see in the movie here, was the first step towards forecasting what was to come next. And so in our 91 JACS paper, we described in 4 sentences at the end what lay before us. And this second sentence I want to quote to you, because the then editor of the Journal of the American Chemical Society prevailed on us to remove all of these comments, claiming they were hype. So let me just read. Insofar as it becomes possible to control the movement of one molecular component with respect to the other in a two-rotaxane, the technology for building molecular machines will emerge. This was the first time that I had mentioned the 2 words, molecular machines. So it was, I think, a good thing to do, to stick to one's guns and not be dissuaded from advertising what was in the future for us. So the next step was to desymmetrize the 2-rotaxane so that you can see the little blue box again jumping between a green unit, which happens to be called benzidine, to a red one called biphenol. And it spends 84% of its time on the green unit and 16% on the red unit. However, you can conventionally, and here you see it shuttling back and forth, more time on the green unit than on the red unit. Quickly, you can change the whole scene by adding some acid, and that protonates the nitrogens of the benzidine unit, and coulombic repulsion sends the blue box entirely to the red unit. And so now we have a switch that is controlled by acid base, that is by pH. And here you see that in motion between a charged unit when it goes to that sort of brownish color, and a neutral unit on the left-hand side when it goes green. I mentioned this 5-catenane previously. This was another feat of synthesis, putting 5 rings together, and you can see that I've picked them out in the colors of the Olympic sign, our Olympic logo. Here's a ball and stick representation, and here's a simplified interpretation of the weak interactions that are present, pi-pi, CHO, and CH-pi interactions in this particular 5-catenane. In other words, it's not just 5 rings linked to each other willy-nilly. They're all speaking to each other in a very, very subtle way. There's another representation of this compound, olympiadine, which was published in 1997. You can see that the group at Birmingham was already very international. At a glance, I can see Italians, Indians, Russians, Hungarians, French, and so on, Germans, and so it goes on. This was game-changing, and of course it breaks my heart today that that country that was England's 2nd biggest city, residing therein, has, as it were, closed its door, roughly speaking, to the influx of people from overseas. Forget about the effect on the economy and all the rest of it, the way it has damaged the lives of young people. I cannot forgive the politicians in England for doing this dastardly act. So, sorry, I get quite emotional about this topic. So come 1997, I had had several offers to move to the States, particularly to UCLA. And for a reason I'll come to in a minute, I did move at the age of 55 to Los Angeles. Changing academic systems presented a very steep learning curve, but I now had extremely supportive colleagues, and collaborations were very much encouraged. And for a period, I became the director of the California Nanosystems Institute, which straddled both UCLA and Santa Barbara. It was a highly productive time. There was much traveling, but I lost my wife in 2004. She had met with breast cancer in 1992, and so for 12 years of a third of our married life, we were fighting that insidious disease. And it was not, of course, a very pleasant time. And it encouraged me later to enter the field of drug delivery systems. I won't talk about those. I will just make a comment about a collaboration with an amazing physical chemist, Jim Heath, who's now the director of the Systems Biology Institute up in Seattle. And together with Jim, during a decade, and this Nature paper in 2007 was, I guess, the peak of our achievement. We put together a 160 kilobit molecular RAM based on a 2-ritaxane switch that you see in the middle, and a crossbar type architecture that was the forte of Jim in producing. Fabricating the crossbar device, I will skip in the interest of time because we're a bit late. And we tested 128 bits, and threw 3/4 of them out. There was only a quarter of them that were really acceptable, but that was enough to produce molecular random access memory at a density of 10 to the 11 bits per square centimeter, which at the time was, and this was 2007, remember, where the International Technology Roadmap for semiconductors hoped to be by 2020. So it was 2007, and out of the blue, I got a phone call followed by this letter from the Consul General, British Consul General in Los Angeles, which was well, a fairly long story, but it was the fact that the Prime Minister of the day in the UK, Tony Blair, had it in mind to recommend to Queen Elizabeth II that I receive a knighthood. This was a huge surprise. It was one of these situations where one wasn't really expecting or prepared for it. However, after being sworn to secrecy for 6 weeks from the middle of November to the announcement at the end of the year, there followed a ceremony, I think it was in June of 2007 at Buckingham Palace, where I met the Queen for 15 seconds, and you'll be interested to hear what was said. So the Lord Chamberlain, who is in the background, his head's been chopped off, said, "May I present Your Majesty to Your Majesty, Professor Fraser Stoddart, for services to chemistry and nanotology. Oh my goodness. Okay, so I was in a cold sweat because I had this very sharp knife on my right-hand shoulder, and when I got up and I looked her in the face, she immediately said, "He got that wrong, didn't he?" That was a big relief. So my retort was, "He certainly did, Your Majesty." And she came back, "What should it be then?" And she got it right, nanotechnology. Good on her. You've got it right, ma'am. So having told her that, she came back with, "It's about very small things, isn't it?" So I agreed with her on that, saying that it was 100,000 times smaller than the diameter of a human hair. That's exceedingly small, and she'd obviously done her homework. She said, "You work in America now, I'm told." And I agreed, and that was the end of our 15-second meeting. I was on my merry way. So it was around this time that I left the UCLA campus and moved to Northwestern, where I am now. Again, blessed with terrific students, great colleagues. As a result of these interactions, lots of publications were flowing and still do. Loads of financial support, too many invited lectures maybe, and fellowship of the American Academy of Arts and Sciences, the National Academy of Sciences, the Chinese Academy of Sciences, you name it, the Australian one. And I served on the honors committee and still do at Northwestern in chemistry. We produced a second book and also brought in to being 2 startup companies. And I got quite involved in philanthropy, which I'll come back to in a minute. The second book on the nature of the mechanical bond is a 6-chapter book. I don't have time to go through all the details. It's over 600 pages in length, and it is very much the heavy lifting was done by an amazing graduate student who postdoced with me for a period while he wrote the book before going to the University of Colorado to his assistant professorship. The startups that I would like to mention briefly are very, very different. One was based on the use of this compound cyclodextrin and second sphere coordination to complex gold in the form of tetrabromoorate as its potassium salt. This is a complex that appears within minutes of mixing it up in water, and so it's ideal for the isolation of gold. And one of my former graduate students from my days in Sheffield, Roger Petman, is the chairman and CEO of the company, and it is thriving now, having spent time in Nevada at the whiskey mine in Arizona. The other startup company is a skincare company coming out of what I call Bob's Your Uncle chemistry. That's a good British phrase. You take a spoonful of sugar, this is a cyclodextrin again, a pinch of salt, better be a potassium salt rather than a sodium one, potassium chloride, and a swig of alcohol, and Bob's Your Uncle. You get this very highly extended structure, and this has led to the establishment of a skincare company called Noble Panacea, which launched just before the onset of the pandemic at the New York Museum of Modern Art in October of 2019. And that was an evening I will never forget, being surrounded by a whole different panoply of stars of a stage and screen that I'm not normally in the company of. It was very interesting. And this has led also to an increased interest in philanthropy. And this is very pertinent today because in the United States, this is called Giving Tuesday. And I am involved in the support of the American Chemical Society Project SEED, which I started championing back in 2018 when they were at their 50th year of being in action. And this program actually supports young high school students from underprivileged backgrounds to explore chemistry in university and college environments during the summer with dedicated mentors. So if I disappear a little today, it's because I will be doing something in support of this so-called Project SEED. Now back to the science. I'm watching my clock, but we're a little late and I better keep going. So the grand challenge, going fast forward to 2012, I would describe as artificial molecular switches are a dime a dozen. Artificial molecular machines, on the other hand, are few and far between because machines need to perform work on their immediate environments. Assembling and controlling synergistically AMMs, as I call them, housed in highly interactive and robust architectural domains, heralds a game changer for chemical synthesis and a defining moment for nanofabrication. And some of the background here is that we're back with these bipyridinium herbicides, or the units, the bipyridinium unit in these herbicides that we had kind of ignored up until 2010. There was plenty of literature that told us otherwise, that we should have been more active from Germany, from Switzerland, Germany, Israel, and South Korea. But eventually, one of my brilliant postdocs said, let's take the little blue box and methyl viologen and kill half of the positive charges and make 3 so-called radical cations. Is it possible that the radicals would win out over the Coulombic repulsion of the positive charges? And the answer was, yes, it did, in a spectacular kind of way. And this so-called radically enhanced now molecular recognition left us with a very powerful way of building molecular machines. So if I define some icons, locks with keys on and off, fairly obvious. Templation, which you've seen already. Radical recognition is associated with the color purple. Remember, I've used blue before for acceptor units and red for rich pi electron units. Now the radicals are purple. We can use heat, that's important in driving our machines, or we can use electricity, and we can have different ratios, and we can use pH. And so now you see in 2010 what was discovered was that if we reduced the little blue box to a bis radical dication and the methyl viologen, the paraquat to a radical cation, then the radicals won out and the complex was formed. This was used to some extent with a so-called energy ratchet that we designed in 2013, where we did use the donor-acceptor red-blue interactions to begin with, and then formed the radical which killed the molecular recognition between the red and blue. And the important thing about this work is that it demonstrates unidirectional motion of the ring with respect to the dumbbell. A few years later, 2015, this led to, the design and synthesis of a molecular pump, where you see the blue box overcoming ultimately in the oxidation phase a green speed bump. The box is brought on by reduction and pushed onto a collecting chain under oxidative conditions. And as you do this, you raise the energy of the whole system in a quite remarkable way. It also led to the design of what was called a molecular joule pump, where the collecting chain in the middle was such that we could isolate a compound, and this is therefore a 2-rotaxane because it's one ring and one dumbbell, and then use reduction and oxidation to push it off the other end. The next one was a molecular Jewett pump, where we put what we now call a pumping cassette on the end of a chain-like molecule with 36 methylene groups and a couple of charged ammonium groups, enough to accommodate 2 rings after reduction and oxidation to push 4 rings in total onto a dumbbell. And that is 4 + 1, a 5-rotaxane. More recently, in the last couple of years, we've gone as far as to take a polymer, which is polyethylene glycol, a well-known polymer, and put pumping cassettes on the end of it, and add 2, and then 4, and then 6, and then 8, and then 10, and ultimately the limit is 12 rings on in a very precise manner. And here's another movie showing you that only 2 come on simultaneously from each end, and we can follow all of this by, again, nuclear magnetic resonance spectroscopy. And most recently, we've converted the long dumbbell into a loop and used, and we need to use 2 rings, starting at 3 o'clock and 9 o'clock, and under reduction going to 12 o'clock and 6 o'clock, and then on oxidation coming back to 3 o'clock and 9 o'clock. So that's a 180-degree movement, and if we carry out this redox chemistry twice, we can have the rings rotate through 360 degrees. And so this is an electric motor. We are anticipating that it will be published about the 12th of January in Nature. So to summarize this journey in terms of molecular shuttles, 91, molecular switches, 94, molecular machines, 2015 and onwards. These are some of the main players on the left and the right. Very, very talented people, and some collaborators, including Bill Goddard, you can see down on the right-hand side at the very bottom. And, oh yes, and I should mention physicist Dean Astumian at the University of Maine. As far as I'm concerned, Dean Astumian walks on water. There is no physicist that I know in the world who understands the way that biomotors and artificial molecular motors work than does Dean. So I pose this question for the young people: what if? Hirst had not challenged me to tackle a big problem. Jones had not gone to Brazil immediately after I arrived in Canada on the 1st of March, '67. Peterson had not introduced crown ethers into chemistry in the April of '67. I had not gone to the ICI corporate lab in '78. I had not met Colquhoun and Williams around the topic of second sphere coordination. ICI had not been marketing Dicot and Parquet as wipeout weed killers. There would have been no blue box, no catenane, and probably no molecular shuttle. My wife's ill health had not taken me to UCLA to the Winstein Chair of Chemistry in '97, and I had not met Heath, that should not be health, sorry about that, Heath, and introduced molecular switches into molecular electronics. The California Nanosystem Institute had not become, this was the reason I moved to Northwestern a bit of a white elephant from lack of financial support, and I therefore moved to Northwestern. My research group had not been visited by serendipity at least twice. There would not have been a couple of startup companies, and not been surrounded by supportive colleagues and brilliant students at, well, UCLA, Birmingham, Northwestern, and even going back to the later days at Sheffield. I had not received support in the US from leading chemists such as Ernest Elio, Kurt Mislow, Donald Cram, David Gutsche, and so on, and in Germany from Helmut Ringsdorf, and in Italy from Vincenzo Bolzani. So here are some of the leading molecular machinists of the day. Let's go back, 2 co-laureates in 16, Nobel laureate Jean-Pierre Sauvage from Strasbourg, Ben Ferenga from Groningen in the Netherlands, and many other people in Italy. David Lee in Manchester, again, Dina Stumian, Steve Loeb in Canada, Joseph Miko, now in the Czech Republic, Eddie Sevek at the ANU in Australia, Mexican, Miguel Garcia Garibay, now Dean of Science at UCLA, Pole by birth, Raphael Klein at the Weizmann Institute, New Zealander Amar Flood at Indiana University, and Ivan Aprahimian at Dartmouth College, and Nicholas Giusepponi, and these are just a few of the new stars on the scene in molecular machine science. A few remarks from Jean-Pierre Sauvage. Importance of novelty over everything else. Interacting with other scientists within your group or outside is essential. Trust young scientists. Jumping from a field, this is what he did, which is very familiar to you, to another field can be extremely beneficial. Do not ask yourself whether you are good enough to tackle a new problem. Just do it. Encounters are determining. Roughly the same kind of message from 2009 Nobel laureate in chemistry, Venka Ramakrishnan. I found that almost nobody at the molecular biology laboratory in Cambridge was working on routine problems just because they would lead to publishable results. Rather, they were trying to ask the most interesting questions in their field and then developing ways to address them. Again, recently, at the early part of the year, I visited what was the Bell Telephone laboratories, and fellow Scotsman Alexander Graham Bell is held in great esteem there, and he has been recorded as saying, "Leave the beaten track occasionally and dive into the woods. You will be certain to find something that you have never seen before." My own take on this, which was published in 2018 in Nature Nanotechnology, to achieve something that is impactful in contemporary science and to be singled out as a scientist who leaves their mark on science and ultimately technologies, you need to become recognized widely as having done your own thing. And the goal, it means, this goal, that you make a very conscious decision to summon up enough courage to tackle a big problem, as I was encouraged by my professor to do, for which no one has provided a satisfactory scientific answer. Message: tackle a big problem. Now, stretching my wings. So in the period from 1980 to 2022, these are some of the countries that I found myself visiting, I think over 50. and ultimately ending up in 2016 in Sweden, in Stockholm, after receiving an early morning call from the Chemistry Committee of the Royal Swedish Academy of Sciences, followed by this letter on the 5th of October 2016, and the prize was being given to Savage, Faringa, and myself for the design and synthesis of molecular machines. The response at Northwestern, which had actually not been very kind to me during the year 2016. I was on the point of moving to Texas without going into any details. But the university hierarchy went through a 180-degree movement, and signage appeared everywhere. I can't go into my office without going past doors with pictures of myself. They took the famous arch at Northwestern and adorned it. We took the opportunity to capture the group at that stage on film. The so-called tech building, which is the center hub for chemistry, physics, mathematics, material science, got that banner placed across it. And most of all, there was this urge to reserve some parking for me. So I still have this parking spot to this day, but I also have a place to park a bicycle because Ben Faringa was boasting in his lectures around the world that Stoddart has this parking spot for a car. I go to work on a bicycle. So I took this as a bit of a provocation, and I got in touch with the president of Northwestern University, and I ended up with a bicycle parking place as well. The problem was that I hadn't ridden a bicycle for many years, but here you can see on the campus of Tsinghua University that I can still ride a bicycle. While we're in China, I had the opportunity to meet former now Premier Li Keqiang, and this was in early January of 2017, and it was reported in Chinese Daily. What you might find interesting is the size of this photograph compared to the size of that one. Atop of the Microsoft building in New York City, they went to town and put up images of my two co-laureates, and I guess myself there. The American Chemical Society adorned the front of their building in Washington with the three of us. And in November, before going to Stockholm, we had the opportunity of visiting the Oval Office in the White House and meeting with President Obama. And then in December, leading up to the 10th of December, we were, as a family, in Stockholm. And on the left and right, you can see my younger daughter and my elder daughter, their respective husbands, and the 5 grandchildren, 4 boys and 1 girl. There was the meeting with the King of Sweden, the receipt of a medal, and additional, whatever they're called, not the real Mackay, but there's a name for them. There are my grandchildren holding the real medal, and here is a...
what a lovely speech that was.
Oh, thank you, thank you.
Well, thank
hope
you.
Meeting with Swedish television.
With, everyone and all those outside looking on. I hope so.
Yes, it did. So, as we can see, you got the advice to bring all the young ones to Stockholm.
Yes.
So, was this good advice?
Oh, absolutely. This was terrific advice. These youngsters will remember these few days for the rest of their lives, and they will I think probably go on with more self-esteem, more self-confidence, and will end up being more successful in their lives as a result of
Future
these-
Nobel laureates.
Yes.
What about you kids? Did you have fun? Did you have fun tonight?
Oh yeah, this night was probably one of the best nights of my life.
It was? Really?
Yeah.
So what was the best thing about tonight?
Eating the chocolates.
Do you agree?
Yes.
What about you? What do you say?
I liked the singing.
The singing was really nice. Yep. Well, thank you so much for joining us, and have a wonderful rest of the evening.
Thank you. Thank you. We can go and eat chocolate. Thank you.
Thank you. Thank you. So thank you, Professor Stoddart, for this amazing presentation and inspiring. I will ask, we are a little bit late, but if there is one question from the audience, from the students, or from some professors or teachers, please, someone can ask only one question. Oh, there is one question there. There is one question there. Just one.
Thank you. First of all, we would like to thank you for the amazing lecture. It's been a pleasure hearing you speak. We found your presentation to be very interesting and inspiring for us as young students. We would like to ask you if you have hope for the contribution and impact that chemistry can have on the world today, especially on problems such as sustainable production of food in a way that can assure the necessities of the global population.
It's the impact of chemistry.
Yes.
Thank you.
So the impact of chemistry.
Okay. I gather the question, because the acoustics are not so good up here, from the hall up to the podium, was about the impact of chemistry. Is that the case? Well, without a doubt, chemistry has a huge role to play. It has played an enormously big role from centuries ago up to the present day. But I put it to you that some of the biggest challenges that we face on planet Earth today, not least of all the results of fairly dramatic climate change, is a problem that by and large is going to have to be and is being tackled every day by chemists. So I think the very survival of planet Earth is not only exclusively, but largely in the hands of chemists. And so I think on that basis, I would say the impact of chemistry is only going to increase as these next few years unfold.
Thank you. Thank you. So, thank you again.
Thank you.
We don't have time for more questions. I'll give the microphone to my colleague. Go, Gadel.
Thank you very much for this fantastic lecture. Now we are going to stop, have a break, so 50 minutes break, and then we'll resume for the last session of the morning. Thank you very much indeed.